So first of the specific types of rate of change questions, and that's to do with growth and decay. And it comes from a basic idea that growth and decay is proportional to population, which makes sense. The more people you have, the more people that die and the more people that are born. So we can say the rate of change of the population with respect to time is equal to some constant times the population. So this is a very simplified version of growth and decay. Well, let's come up with an equation then for population. As P is the pronumeral, I'd rather have this with respect to P rather than with respect to T. So I'll turn it upside down. I now have the T to P. And so I can work out then that T then would be 1 on K times the integral of dP on P. Well, dP on P, integrate that, we get log P, plus, of course, a constant. So we now have an equation for time, but we want an equation for population, so we need to rearrange this. Multiply by K. Notice I didn't bother multiplying the constant by K because constant times constant is still a constant. KT is log P plus a constant. So the log of P is KT minus a constant. So to undo the log, we exponentialize, and we get e to the KT minus C. But I'm going to play around with my index laws here, because e to the minus C, again, would just be some constant. So I could rewrite it as P is equal to some constant times e to the KT. Now, the thing is, with these growth and decay questions, you don't actually have to go and derive this, which is one of my big criticisms, of course, is because this topic is part of what's called applications of calculus. But hey, don't worry about using the calculus. Take all the fun out of it. So we can jump straight from, well, if we see that the rate of change to P to T is equal to some constant times the population, we can just go, oh, well, we know that P is equal to AE to the KT. P then represents the population at any particular time. A will end up being the initial population, if you think about it, because if you sub in T equals 0, well, then you'll end up with e to the power of 0, which is, of course, 1. So A would be the initial population. K is our growth, or if it was negative, decay constant. And T is, of course, representing time. So we're going to have a look at some little bacteria here. And the rate per hour of the population growth, it's 10% of the population. And the initial population is, how many zeros have I got there, is 1 million. So we've got 1 million of these little pieces of bacteria here, and they're growing at 10% per hour. So what they tend to do, rather than say, they don't actually get you to derive it each time. They tend to start off with something like this, just show that this would be a solution. And rather than derive it like I just did, because it's a show that question, the quicker way of doing it is just differentiating that. So I have A, which remember is a constant, e to the 0.1t. So differentiate the exponential, well, the power, differentiate that, we get 0.1. So I have 0.1 times AE to the 0.1t. But of course, AE to the 0.1t is P, and we end up with 0.1 times P, or a constant times P. So it satisfies the differential equation of P to T is equal to some constant times the population. We're now going to work out the population after 3.5 hours. So we're starting off with 1 million little gooby wobs. How many have we got after 3.5 hours? Well, what do we know? We know that when T equals 0, the population is 1 million. So I know that A is 1 million because that was representing initial population. I can now simply substitute in. So T is 3.5. Rounding off, of course, it's not exact, but they said 4 significant figures. 1,419,000. So after 3.5 hours. Okay. On an island, population in 1960, 1,732. In 1970, 1,260. These people don't like each other. Okay, it's going down. Find the annual growth rate. Well, in reality, it's going to be a decay rate, assuming it's proportional to population. So, okay. We're assuming p to t is equal to some constant times p. And so we can say, oh, well, the solution to that is p is equal to ae to the kt. Now let's find some of these variables. Initial population is 1,732, so we know a is 1,732. We now need to work out k, because that's what they're asking us to find. Find the growth rate, find k. So we know that after 10 years, the population's 1,260. So subbing that information in, and well, we've got an exponential equation to solve, but we just need to find k. So I'll divide by the 1732, undo the exponential by logging, and then dividing both sides by 10. That would be the exact value, of course. They've said to the nearest percent, and remember it's natural logarithm we're using here because it is e to the power of. That works out to be negative 0.031865, etc., etc. But to the nearest percent then, it would be negative 3%. So growth rate is negative 3%, or I suppose you could say the decay rate is 3%. So, in how many years will the population be halved? That of 1960. So 866, that is half of 1,732 for those who were unsure. So e to the kt will equal a half. Rearranging that again, making t the subject, we get 1 on k, the log of a half, which also happens to be the formula to work out the half-life of radioactive material for those that do, what's that in chemistry? No. So that's basically where it comes from, this sort of idea. Okay. Now, I haven't bothered writing out the k, it's just that value we found before. I've stored it in my calculator, but when I punch the buttons, I get 21.786. So it says, in how many years will it be half? So 22 years. It is normal rounding here. Had the answer been 21.3, I personally would still say in 22 years, because once 21 years is arrived, it hasn't been halved yet. So it would take 22 years until it was halved. But as long as you justify your rounding, I don't think that's going to be a big issue there. Okay, 7G. We shall try, how many have I got in there? 1, 2, 3, 4, 6. 6 different questions to have a look at. Yeah.